Hi friends, my name is Arun Bhatia and I am the CEO and consultant of Luminescence Technologies, which is located at Gurgaon in India. Today I am here to make a presentation on DOB LED lighting solutions. So welcome to you all. So to introduce what we are talking about, the driver is a critical and essential part of the LED lighting product. Well, basically, an LED is a low voltage device typically working at 3 volts DC. However, the products that we need should work from 110 volts AC or 230 volts AC input. So, the driver is required to convert the high voltage AC input to a low voltage DC for driving each LED at a controlled voltage of say 3 volt DC and pass a controlled current of say 60 milliamps into the LED to preserve the long life expected from the LED product. Now here's the basic scheme showing the role of the driver. At the left side we have the input AC 230 volts or 110 volts as the case might be, which goes to the driver. The driver converts this high voltage AC input to low voltage DC at a precise controlled current, which is then fed to the LED module. So to give a rundown, well, I have listed here 5 types of LED drivers. The first type is a resistive one. The second is a RC driver. The third type is a linear driver. The fourth type is a switching driver. And lastly, I've put here the driver on board or DOB. So here is a schematic representation of the resistive driver type. AC input is fed to a diode bridge which converts it to high voltage DC. This is then fed to an LED through a resistance R, and R actually takes the voltage drop between the high voltage diode bridge and the lower voltage LED, and depending on the value of resistance chosen, we have a certain current being driven through the LED. This is a simple approach, and if you like, we can put the capacitor to filter out the ripples. However, the drawback is that there is a lot of power loss in the resistor, and only a fraction of the power is actually fed to the LED, which is not desirable. Then we have the RC type, which is actually the capacitive type, and this capacitive type, we choose a capacitor whose impedance at this frequency of 100 Hertz ripple is just right to feed the desired current to the LED. Resistance is placed to act like a fuse or limiting of the current and assist the capacitor. However, the main role is the capacitor. And what is to be noted here is that there is a phase shift, and the current here is actually in a leading mode, being a capacitive circuit. But the good point about this circuit is that the efficiency is good because C does not dissipate any power. It stores the energy within itself, and this circuit was very popular some time back, and even now, right now it is still used in simple low wattage applications. On this slide we have the linear driver, and in this what we can see is that we have a regulator which comprises of a Zener diode and a transistor, and this regulator actually buffers the changes in input AC fluctuations from the output. So while this is very good for the input AC regulation, but it still is inefficient because a lot of power is actually dissipated by the series transistor being used here. Now here is the most important driver and the most popular driver being used today. And it's a beautiful solution which is called a switching driver. The trick here is to avoid any energy loss by just switching the high voltage DC on and off. So we take a little energy from the input and store that energy for slower consumption within the inductor L1, and there is an output capacitor C4 which acts like a filter and smoother and for saving energy in the meantime. And this kind of switching driver usually switches at a frequency of 60 to 100 kilohertz. So here we have a driver that is efficient, accurate, has input to voltage regulation and includes all the protection and is high power factor. So this is one of the best solutions being used popularly today. Now one may ask that if that is really the case, then what are we really missing? Why do we still need a better driver? Or why is there still a need for improving the drivers? Well, I'm giving here three important reasons. The first one is that electrolytic capacitors which we use in these switching regulators have a finite life. So if we have a capacitor which is rated for 5000 hours and we are trying to give a 2 years warranty, well, if the temperature is not controlled very carefully, this particular 5000 hours might exhaust in 208 days only if the driver or LED product is kept continuously on, and that's not sufficient. So if we have to give a 2 year warranty, we have to handle this challenge of the electrolytic getting failed within those 2 years. The second important reason is that when we are switching at 100 kilohertz, there is an electromagnetic interference which needs to be filtered by means of using inductors and capacitors, and this increases the complexity further, increases the cost, increases the number of parts, and requires labor, which itself has an additional cost. Then the third factor I want to list here is that these inductors which we are using in these switching regulators, and you see we can't do without these in the switching regulator. The thing is that inductors can really not be made easily with full automation. They have to be manual or semi-automatic processes, and in that case, one, the cost goes up, it is cumbersome, it is difficult to make, it has a cost, and also since it is not fully automatic, there is a finite failure ppm which has to be reckoned with. And so these three factors really leave something to be desired. So here we, with that thought in mind, we come to the DOB, and here I have put a rough schematic on this concept. So after having a bridge rectifier to convert the AC to DC, we have this rectified DC voltage which is shown above, and that goes to a string of LEDs. Typically I have shown here 4 banks of 3 LEDs each, So that is 12 LEDs in all. And after each bank, we have placed a MOSFET switch. So you can see 4 switches. This is what we call a 4-channel DOB solution. Now there is an IC which may include the MOSFETs themselves, and which also would include the current sense logic. So we would have a current sense resistor which monitors the current emanating out of all the 4 channels together, and the IC actually controls at which time it is going to put which bank on. So if you see the markings on the wave sinusoidal half wave shown above, we have the marks of bank 1, bank 2, bank 3, bank 4. So these are marking the points where the particular switch will be on or off. So to start with, when the waveform is at its lowest point near 0 and it starts rising, we have just the first MOSFET becoming off, and then we have the second MOSFET going off, then we have the third MOSFET going off, and then the... So what really happens is that as the voltage climbs up on the sine wave, we get more and more LEDs into the picture facing the actual voltage coming from the bridge. So it's really in a way that it's switching depending on the current position of the voltage. We have that many LEDs coming into play, and that is how this regulator works. There is no high frequency switching. Now with this solution, the kind of waveform that we will see of the light output, which actually is the current, total current flowing into the LED module, would look something like this. So you can see that this waveform would be in phase with the voltage, so it will be high power factor, and it would control the current going into the LEDs. Now you can have a number of channels, 1, 2, 3 or 4, and a very popular solution which I'll show you on the next few slides is with 3 channels. And the more the number of channels, the more the complexity and cost of the IC. That is what we have to remember while designing. Now the salient features which I'd like to list for a DOB driver are low parts count and simplicity, low cost, no inductors, no capacitors, no need of separate driver PCB, high reliability, high power factor, low THD. When integrated into the LED MC PCB, it has good thermals and good life. Since the concept is essentially of a linear current control, there are no current spikes to harm the semiconductors and LEDs. There is no high frequency present and system works on pure 50 Hz soft linear mode. No inrush currents can be used in dimmable solutions also. Since the basic current control is linear by means of resistor, these drivers are also referred to as linear drivers. Now here I am showing you one example of DOB IC, which is made by Bright Power Semiconductor, and this is actually a 700 volt MOSFET, and it has 3 channels, D1, D2, D3, and all the controls. There are of course other companies which are also manufacturing their own versions or similar devices. Here is the example schematic of a solution using that PP Semi IC, and you can see the 3 banks, and you can see the 2 resistors. One is the current sense and one is a resistor which controls the current based on the feedback of the voltage which comes from the input voltage, and then you have the bridge rectifier. This is the block diagram of the same solution, and here you can see that these are the D1, D2, D3 outputs which are coming from the internal MOSFETs, which, as I told you, are 700 volts rating, so it's very high, and so this circuit is got a lot of safety and reliability. And these are the reference inputs which are compared and based on the current sense, which is again input from the resistor. These switches are controlled on and off, and this is the line compensation point, which is again connected to a resistor, as we saw. Now this is the example of the operation. Basically the operation starts when the D1 voltage climbs above 10 volts and the IC goes into normal functioning. Now what you have to remember is that the LED strings have to be chosen such that the total forward voltage of this string, total string, is 110 volts or 220 volts or near about, as the case may be. Now here is the formula. How do we configure the current for this solution? And we must also remember that there is thermal regulation also available on this IC, and since it is placed on the MCPCB, it actually, when the temperature crosses 140 degrees C, it starts controlling and bringing down the current and power to the LEDs, and thereby tries to keep the system going beyond a certain temperature. And this is the calculation which we need to do to determine the current compensation resistor. This one, and this is the formula that we will use. Now what are the components really required? So in summary, here is an example DOB solution PCB on the right hand side. The essential components, as we can see, are the bridge, the IC, and two SMD resistors. Now if you want to make the solution more advanced, that means it has to face more difficult power situations, then we can add a fuse resistor and an MOV into this for safety and longer life. Now here we can see a board which has these two components incorporated. You can see there's a fuse resistor and there's an MOV, and the LEDs are kept surrounding the DOB circuitry in the middle. Now this of course depends on the kind of product we have in mind, what we are designing, and sometimes it so happens that we cannot keep the center region blank, or we need the LEDs in the center. So then that is a challenge which designers need to solve, and that is where some problem might come, how to solve this product elegantly. Now this is a presentation where we are showing that how to design, how to go about the designing of such a product. Now the first step is that we choose the LED string size by number of LEDs and VF, the forward voltage, such that the string voltage matches the input voltage, like 110 volt or 220 volts approximately. Next, we choose from the available VF of the LEDs. That could be 3 volt, 6 volt, 9 volts, 18 volt, 13, 36 volts, etc. Now these LEDs can be either low power, 0.5 watts or 1 watt typically. This means that for 220 volt design, if we are designing a bulb or small downlight with 18 volts LEDs, we could use say 12 LEDs. Next, structure the banks depending on the number of channels available in the IC selected. If we are using BP5336H, for example, which is a 3-channel driver, and we wish to make a 6-watt downlighter, we would use 14 LEDs, 18 volts, half watt LEDs, and string them in a bank with 9, 3, and 2 LEDs. This would yield VF bank points as 162, 216, and 252 volts, for example. On the other hand, if we wish to use the same IC to make a 6-watt panel light, we need to use more number of LEDs as the MCPCB size is bigger now. So we can decide to use total string of 24 numbers of 9 volt LEDs instead of 18 volt LEDs and make banks of 8, 7 and 5 LEDs. This would yield VF bank points as 72, 135 and 216 volts, for example. The important point is to realize that if the light being designed is a nearly point source like we have in bulbs, downlights, spotlights, floodlights, we can easily place the DOB anywhere on the MCPCB. However, if we have wider MCPCB area lights like panel lights, ceiling lights, etc., we have a problem in locating the DOB components, particularly if we need safety components like fuse resistors and MOV on the PCB, as these will create dark patches in the lighting. So that becomes a challenging factor when we are designing products in which it's not like a very small point source. Another approach is to split the safety components to a secondary board, which can accommodate, say, the fuse resistor, the bridge, and the MOV. In this case, we can also use 2 fuses for even better performance. So here is a depiction of this scheme of things. We have a separate FR4 PCB which accommodates the 2 fuse resistors and an MOV and a bridge, and gives a DC output which is safety protected and which is then feeding the MCPCB, which has the DOB IC on board along with the LEDs. So this is a 2 PCB approach, which is a little more expensive because you need interconnection, some small wires to connect from the small board to the MCPCB. So it slightly pushes up the cost. But then it's a, if you want to make a more durable product, then this is one approach which can also be adapted. Usually a single DOB IC will handle up to 10 watts or so maximum. We do have DOB ICs which can handle more power, right up till 25 watts also. For higher wattage products, we can use multiple DOB ICs on the MCPCB. Like for example, we have shown a floodlight PCB on the right hand side. This picture shows the DOB solution, which was a one single bridge along with 4 DOB driver ICs, and the whole combination is capable of handling 100 watts floodlight solution. So in summary, DOB lighting is here in a prominent way to make LED products simpler, reliable, longer life and cost effective. So let us consider DOB solutions in new lighting applications in an innovative way. You see, DOB technology has been here for quite some time. but it was not able to get itself adopted into many products, particularly in countries which have 220 volts main supply. It's easier to implement in 110 volts and a little more difficult to use it in 220. But now, with the improvement and simplicity and cost affordability of the new ICs that have become available, the DOB solution, as we have seen in this presentation, are now a very attractive alternative. And as designers, we must all consider, can we use this for cost effectiveness, for durability, and for elegance and simplicity of the design? We must remember that at the end of the day, it's not the pure specifications of the product that are most important. It's also the life factor. You see, LEDs basically are touted as the high life, long, long durability and life products. But the weakest link in the chain we have noticed in most of the products today is the driver. The driver specifications are excellent, they look beautiful to designers, but end of the day, do they deliver what they promise in terms of life and durability? Do they make the system weaker? And do they become the weakest link in the chain? If we keep these thoughts in mind, we will feel that indeed today, driver on board, or DOB solution as we call it, has indeed become a very viable and important category of drivers for good LED products. Thank you. Thank you all. If you need any more information, you can always get in touch with me. My website address is arunbhatiaconsulting.com. Thank you and have a nice day.